In the world of mineral assay, errors can and do occur. Either human caused, instrumental faults, and others. The combined results of the combined analytical quantified elemental concentrations from the lab and the statistical results will be in error. There are methods to determine the accuracy and the precision of the final results. In this presentation, a few of these methods are discussed. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. There are times when you may want to take duplicate samples. This results in duplicate measurements. Duplicate samples are taken from a larger sample after the sample has been thoroughly mixed, that is, homogenized. Now in the lab, this would be done to evaluate the analytical methods used to determine the final results. Due to the nugget effect and other induced errors in sampling and so on, the standard deviation and the population deviations, which are also referred to as the mean deviation, will vary and some quite significantly. In this example, a hypothetical sample was taken from a concentrate pile and carefully split into two duplicate samples. You can easily see the statistical results are different. It may show that the mixing method used may be the method that is inducing the error, or it may simply be the nugget effect. If it is a nugget effect, then a method must be used to more accurately represent a truer picture of the duplicate samples. An F-test should be done to determine which is which. This simple test will be covered later in this presentation. So let's continue. Duplicate measurements are usually taken to discover and maybe quantify the errors, if any, in the sampling, methods of analysis, and or other factors that may introduce these errors. Duplicate analysis is a means of checks and balances. As shown, for simplicity, two sets of samples were taken, 6 samples per set. The first sample is designated XA and the second XB. D is the difference between the samples of each set as laid out in the table. A D squared is just the square of the differences between the two. The equation shows that the standard deviation of the duplicate measurement is the square root of the total squared difference divided by the degree of freedom. In many textbooks, V is commonly used for K. Therefore, V equals K, and K simply refers to the degrees of freedom. Since we are dealing with samples only, the degree of freedom is simply the total number of samples combined from both sets. In this instance, it is 10, which is 2 sets of 5, or 2 times 5 equals 10. But as you can see from the table, we may have some outliers, and the curve would be skewed. Mining laboratory technicians will take 2 duplicate samples and compare the results. This is done to check on the calibration of their equipment or the methods used for sampling, and or contamination from sampling equipment. As for the small-scale miner or prospector, you may want to do your own checks to see if your equipment is functioning correctly. Equipment such as your electronic scales and other measuring devices. Most of you will not be conducting any solutions chemistry for instrumental analysis. In most instances, you may be doing it for fire assay techniques or sieve analysis. If this is the case, then a single duplicate may be taken and the result between XA and XB will be used to identify if errors are induced. There are a small number of tests that are applied. The math behind these tests is not difficult and mostly straightforward. However, reference tables will be required. Tests such as the F-test, the Q-test, the student's t-test, as well as ANOVA will be discussed later in this presentation. Before moving on, I need to talk about 2 small but important items. This slide is the first of a few. Both of these diagrams give the same information. The red line in the picture on the left represents the mean line. The green dots are the individual results of the many samples taken. Each dot is the analytical result of each sample. It shows how much the dots deviate from the mean. The picture on the right has the mean, being the red line, in the center of the graph. It is listed as 0. The curve, which is flipped by 90 degrees, shows where the mean, or how it may have deviated from the calculated mean, on the positive side. It corresponds to the graph adjacent to it. A curve, which would also have been drawn on the minus side of the graph, if it was added, it would show how much the entire curve would or could have deviated from the mean, that is the calculated mean, on the minus side. Hence the plus and minus. Coefficient of variation is the same as relative standard deviation. Both terms are interchangeable. It is calculated as being the standard deviation divided by the mean. Applying some hypothetical values as shown, the relative standard deviation is 0.077, or rounded to 0.08. It could also have been stated that the coefficient of variation is equal to 7.7, or 8.0%. What is important here is that any reporting value given will have a plus or minus value attached. If this was a gold estimate report, it would be reported as 6.05 grams per ton, plus or minus 0.08 grams. The other important subject is more of a concept. To start with, the confidence level is a value that is stated and picked by the person conducting the statistical analysis. It is a statement. As depicted here, the statement is given. It states that the mean given is 95% accurate. There is, however, a 5% probability that it may not be so accurate. The interval is a range of values. These are used to describe the uncertainty or variability of the population parameter, which is usually the mean. Something referred to as the standard error of the mean is the same as the confidence interval. If the sample or samples taken were a large portion of the material sampled, then a finite population correction would need to be done. The standard error is a simple calculation and is equal to the standard deviation divided by the square root of the total number of samples of the sample set. If the total number of samples amounted to a significant portion of the material that the samples were taken from, then the finite population correction value is used. Here's how it would come into play. Let's say we had 300 sample bags that were brought in for analysis and composited into one large sample, changing it to be a population, one large lot of material. Let's say that out of this lot, or population, 30 samples were taken. The sample mean error was calculated and reported as 1.5 grams plus or minus 0.016 grams. Now that would be just for the sample set. However, for the population, due to homogeneity and other induced factors during the process of collecting those 30 samples, a correction will need to be made in the estimate of the population, which is based on the sample set taken. At this point, a value from the student's t-table, commonly referred to as just the t-table, must be used. For a 95% confidence level, the t-value is 2.0452. The value for the standard deviation was shown to be 0.08955. The sample size of the set is relatively small, however. When dealing with a population, a more accurate estimate needs to be reported along with a confidence level and interval. Therefore, the report would state that the mean with 95% confidence is 1.5 grams plus or minus 0.03 grams per 300 kilograms. That is, if that was what the total weight of the 300 bags weighed out to be. The 0.03 would be the interval level. As for the confidence limit, they represent the upper and lower values of the sample set. as shown on the curve. Houston, we have a problem. Now that has always been a famous statement, but in analytics, it's a truth. Tests are statistically done to discover problems that are inherent and are caused by the person conducting the analysis. There are basically 4 tests that are performed, most of the time. The first is the F-test, and it is used for testing dispersion. As you already know, if you have been following along, standard deviation is dispersion. It basically looks at the dispersion between 2 standard deviations. It is not only used to look at 2 samples from the same population, but can also be used to compare 2 populations. More on this later in this presentation. Now, there are 3 student t-tests that are available. These are routinely conducted. First is the one sample t-test, and it is used to test the sample mean of a sample set against a population mean if that population mean is known. The second is the 2 sample t-test, which is used to compare the results from 2 different analyses or methods, or 2 different populations, which would be similar to the F-test. The paired sample t-test, which is the third t-test, is used to compare the sample mean of a sample set to that of a population where the mean of that population is not known. The last available test that may be routinely conducted is ANOVA. It is used to compare 3 or more groups of data. Mathematically, it is a little more cumbersome, although the math is relatively simple. So let's start with the F-test. As stated in the previous slide, the F-test is used to test the equality between 2 populations. Let's say you were looking at purchasing a claim, and the seller allowed you to do some analytical testing to prove the concentrations that he states is on his claims. In this example, it is assumed that the person had 2 cells. You conducted 2 sets of grid sampling, 1 set from each cell, and you wanted to compare the results. Is the concentration of each cell the same, or are they different? An F-table similar to the one shown is used, and the math is simple. The F calculated value is calculated by taking the first standard deviation, which is always the larger of the 2 for the numerator, divided by the second standard deviation. As shown, the F-table critical value is 3.39. The calculated F value from the sample is 1.4307. Since the critical value is less than the table value, then you can say with 95% confidence that the 2 populations are the same. If those average figures were representing roughly 7.4 grams per ton at $2,800 per troy ounce at the time of the making of this presentation, it may be well worth acquiring the claim being offered for sale. Before I move on, there's a few items that need clarification. As the next few slides will show, the example given will be for a 2 sample t-test. The example will contain 2 different numbers of samples in each set. I quickly discussed earlier the concept of the degrees of freedom. Most of the time it is more convenient to do a 2 sample test with equal numbers of samples per set. This way, each sample set will have a degree of freedom equaling to n minus 1. And since there would be 2 sets, then the degree of freedom would be 2, and so on, as more sets are added. The formula shown is for sets that do not have an equal number of samples per set. This will be shown on the next slide. Take note of the t-table shown, especially the top 3 rows. It comprises of a cumulative probability row, a one-tailed test row and a two-tailed test row. The cumulative row shows a t.975, and below that is 0.025, and below that is 0.05. Now that would be the column that would be used for a 95% confidence level. The t.975 stems from the 0.95, which is 95%, plus 0.025, which total is equal to 0.975, and with 8 degrees of freedom, the critical value is 2.306 as circled. That is how the table is read. Now for that little item at the bottom here. It is the formula shown in every textbook. Now the bar D simply represents the average value of a given difference between samples. The bar simply represents average. The plus or minus symbol is simply the plus or minus value given, and that TA divided by 2 part of the equation, highlighted in blue, simply refers to the first 3 rows of the table. It simply points to the two-tail row of the table. And if there was a 0.975 attached to the end of it, it would specifically point to that row and column. In this example, the T critical value would be plus or minus 2.306 as illustrated. Assume that a small-scale prospector has a 6-cell hard rock claim, and he has found some gold-bearing veins on the side of a mountain. On one cell, he took 10 samples out of the hard rock and had them analyzed. He also took 9 samples from an adjacent cell as well. He needs to compare the two to find out if the results are as close to being identical. Are they from the same vein complex or structure? First, he needs to determine what the degree of freedom that he will use for the analysis is. All calculations are shown in the table, and the formula that was introduced is the one we will need to use. As presented, the standard deviations are squared, then divided by the respective number of samples in each of their cell sets, and then further divided as shown. Notice the degrees of freedom per set, which is n minus 1. Following through the calculations, we end up with 8.00616. Unlike the rules for rounding, to obtain the degree of freedom, we would round down, not up. With our example here, it is 8 degrees of freedom. It would be written as DF8, P05, T critical equals 2.306, as I have indicated on the previous slide. Before going into the 2-sample t-test, I want to start with a discussion on a single-sample t-test, sometimes referred to as a 1-sample t-test. As stated previously, the 1-sample t-test is used to compare a single sample set to a known population. Are they the same? If a series of previously tested sample sets resulted in a mean of 8.23 grams per metric ton, and you wanted to know if the sample set actually captured the population mean, the single sample t-test would be used. For example, if a small-scale miner was looking for a partner to help further advance his mining operation, and he told you that he was getting an average of 8.23 grams per metric ton, you would want to see for yourself. The t-test is one way to find out if he's actually being truthful. This is a test that can be performed. As shown, there are 10 samples in the set. A mean and standard deviation have been calculated. We would also need to perform a correction in order to show where the upper and lower limits would be for a 95% confidence level. A student's t-test table is required, as shown. The t-critical value at 95% confidence level with 9 degrees of freedom is 2.262, which is highlighted with a circle. The critical region for rejection is calculated by multiplying the standard deviation of the population by the t-critical value. As shown here, the standard deviation of the population is calculated by dividing the sample set's standard deviation by the square root of the number of samples in the set, in this case, 10. The rejection region is the upper and lower confidence limits to the set, or of the set. To obtain the plus and minus value, we simply multiply the t-critical value by the standard deviation of the population. In this scenario, it is 0.5919 or 0.592 rounded. This is your plus and minus value. Calculated t-value for the set is calculated by subtracting the mean of the stated population from the mean of the sample set, then dividing it by the population standard deviation. As shown, the upper and lower confidence level limits are 7.048 and 8.232. Anything above the upper confidence limit or lower than the lower limit would be rejected. Since a calculated t-value is lower than the critical level, we can say with 95% accuracy that the sample set represents a population. We can also say with 95% accuracy that the mean of the population is captured within the upper and lower confidence limits. Let's expand the example a little. Assume that a small-scale miner, having a mineral claim across a large section of mountain terrain, and in one cell he located a gold-bearing quartz vein. 2 cells over, he located another gold-bearing quartz vein, and he wanted to know if there was a significant difference between the two. Now, they may be linked geologically from the same vein structure. To find out if there was a significant difference between the two, he took 10 grab samples from one and 9 grab samples from the other. The calculated results are shown in the two tables. A pooled standard deviation had to be calculated first. To a statistician, there is a lot of theory as to why this is done, and therefore I will not bore you with a lecture. But pooling the standard deviation gives a more accurate estimate when dealing with multiple samples. As shown, the pooled deviation is 0.644. The t calculated is similar to the single sample t-test. The only difference is now we are comparing two specific distributions, the bar x1 and the bar x2, which is divided by the pooled deviation value of 0.644. We then multiply the resulting value with the results calculated using the number of samples in each set squared. The final result is 0.946. For the table value, the degrees of freedom is shown. From the table, the critical value for a 95% confidence level is 2.110. Therefore, we can say that with 95% confidence that there is no significant difference, and both quartz veins may very well stem from the same internal geological structure. This is just another example of how the pooled standard deviation is used to keep track of the trending results. Each week one could take a set of samples. Dates are shown. The degrees of freedom are shown, but take note of that column. In some textbooks, DF is designated as V. When it is tabled in this fashion, it becomes easy to calculate the pooled standard deviation, the average of the population, as well as the plus or minus of the average. As depicted, the average concentration in the last 5 weeks was 3.1 grams plus or minus 0.1 grams per ton. ANOVA is an acronym, which simply means analysis of a variance. Although the term variance is used, it is actually used to determine if there is a difference between two or more population means. The table represents this example. Assume that this hard rock miner, I'll call him Billy Barker, claimed a dozen cells on the same mountain, next to the previous miner. He located 3 nice-looking gold-bearing veins and took 8 grab samples from each outcrop. He needs to know if all 3 veins are equal. He chooses the ANOVA test because there are 3 separate populations. Shown is the table with all the initial calculations completed. For ease of calculation, the table was constructed using Microsoft Excel. For the critical value, the F table is used. This is depicted by the F in the ANOVA equation. Notice how the table is arranged. There are 3 groups, assays 1, 2, and 3. Since there are 3 groups of 8 samples in each set, the total number of samples will equal 24. There are terms in the textbook that refer to entities. There is sum of squares within and sum of squares between groups. Hence the terms DFB and DFW, within and between. Both are calculated as shown and are used to obtain the F critical values from the table, being the degrees of freedom between and the degrees of freedom within. The mean T value is the mean total value, which is the mean value or average of the 3 assay means in the table. You know now what N and G are in the ANOVA equation shown. But what is SSW? What is its value? Well, this is a simple calculation. However, it is tedious. It is simply a total of each sample minus the respective means squared. The dots in the equation simply states that you keep adding each of the samples up until the end when they are totaled. X1.1 refers to sample 1 in the first set. Mean 1 is the mean of the first set, and so on, all the way up to X3.8 and mean 3. X38 is the 8th sample in the third set and its respective mean in that third sample set. As per the previous slide and the one to follow, the table was created using all the functions in Microsoft Excel. The sum of squares between is also a simple calculation, but also somewhat tedious. You have the 3 groups consisting of the 8 samples each. Each group has its own mean. In addition to, there is that mean T or total. Now the T in mean T is not the total of the means added together. It represents the mean of the 3 means. It is the average value of the 3 means as shown on the table on the left. Also take note that the calculation in the table on the left are rounded. The calculations for SSW and SSB use the more precise values. As the equation states, SSB is equal to the mean of the first set minus mean T squared, which is then multiplied by the number of samples in that first set, and so on. As calculated, the table shows an SSB of 0.003, 608333. So let's move on and put it all together. Now we can calculate the F value. At this point, we can round the figures. The SSB rounded is 0.004. SSW is 8.854. We know what N is, which is the total of the 24 samples. And since we have 3 groups with 3 degrees of freedom, that will equal to 21 for the n minus g value. We only have 3 groups, and therefore with the 1 degree of freedom, the denominator becomes 2. As shown, the F value is calculated to be 0.009. Now, we need the F table. And using the F table, with 1 degree of freedom equaling 2, and the other DF2 equaling 21, with the 95% confidence level from the table, it is 3.47. Since the F calculated value is less than the critical value of 3.47, with 95% confidence, there is no significant difference between the 3 populations, and that the 3 sample sets may actually be from the same population. So let's take a look at the F table. This is a look at the F table. You can find a free set on the net, and they are also printed in the back of most engineering and statistical textbooks. The top row is defined as DF1, and the vertical column on the left is DF2. Notice the circled value in the example. It is 3.47. The table at the top signifies that this table has a probability of 5%, which translates to a 95% confidence level, with DF1 being 2 degrees of freedom and DF2 being 21 degrees of freedom. We have an F critical value of 3.47 and would be represented as F critical. DF1 equals 2, DF2 equals 21, and 95% confidence, 3.47. Well, this concludes the series titled Secrets of the Gaussian. This 4-part series was put together for the small-scale miner, prospector, or hobbyist who wishes to upscale his recreational endeavors. It is a simplified series created to help anyone wanting to purchase a claim, sell a claim, or simply wanting to stake a claim. Statistics is used to make the decision. Is it worth it? If you have followed along throughout this 4-part series from the beginning, you should now have the knowledge to conduct your own assessment. This series was not intended as a complete course on statistics. It is a cut-down version for those that have not been introduced into the subject matter. If you found this presentation of interest, know of someone who may benefit from this edited video presentation, please give it a thumbs up, a like, and a share. It's my only reward. I'm Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.